Pluto is a fascinating and enigmatic world that lies beyond Neptune in the Kuiper belt. Although it was once considered the ninth planet in our solar system, it was reclassified as a dwarf planet in 2006. From the start, Pluto has stood out as an unusual celestial body due to its orbit, which intersects with that of other planets, something not typically seen in planets. However, this uniqueness has only fueled further interest in Pluto, especially as we explore the cosmos in the search for life. Once thought to be an inhospitable region of the solar system, Pluto has revealed itself to be far more intriguing and potentially promising than previously imagined. Discoveries on its surface and beneath its icy shell have exceeded expectations. Stunning images captured by NASA's New Horizons mission in 2015, along with other observations, have challenged old perceptions of Pluto, showing it to be much more than just a dwarf planet. These findings have puzzled scientists, as they do not align with prior understandings. As we delve deeper into Pluto's mysteries, we are confronted with questions about its size in comparison to Earth. Is Pluto as small as 1 to the power of 3, 4, 5, or 6 relative to Earth? This questioning invites us to reconsider the true nature and size of Pluto in the universe. One of the most compelling theories is the existence of a liquid ocean beneath Pluto's frozen surface. This theory gained traction due to the presence of extensional fractures and the lack of large craters in certain areas, suggesting more recent geological activity than expected. Though the idea of subsurface oceans on celestial bodies beyond the gas giants is not new, having been discussed in scientific publications since 2006, the arrival of NASA's New Horizons mission in 2015 provided fresh details and spectacular images that fueled further speculation. When the probe reached Pluto, it provided the first detailed look at one of the solar system's most perplexing objects. The images revealed a surface marked by a network of cracks, ice volcanoes, and a massive, heart-shaped basin. These discoveries have led some scientists to believe that even more astonishing phenomena may be hidden beneath the surface. For instance, the analysis of the images uncovered a large icy basin called Sputnik Planitia, located in a position directly opposite Pluto's largest moon, Charon. While this could be a coincidence, the odds are low. Only 5% of models suggest this alignment could be accidental. When the basin formed, there may have been a subsurface ocean that played a role in shaping it. Later, nitrogen gas present in Pluto's atmosphere cooled and settled in the frozen basin. The accumulation of additional water and ice created a heavy load that caused Pluto to tilt into its current orientation. The concept of an ocean beneath the surface has remained a persistent idea, and images of Pluto's far side have only strengthened this hypothesis. Strong evidence has been found, including a feature known as chaotic terrain, which consists of fractured and jumbled blocks of ice. This region is located on the opposite side of Pluto from Sputnik Planitia. Similar phenomena have been observed on Mars, Mercury, and Europa, one of Jupiter's moons, where the impact of an asteroid or comet is thought to have generated seismic waves that converged on the opposite side of the body, creating chaotic terrain similar to what is seen on Pluto. Alden Denton, a graduate student in planetary geology at Purdue University, simulated how an asteroid impact could send shock waves through the dwarf planet. These simulations presented a scientific coherence, suggesting that such a collision would only have been possible if Pluto had a liquid ocean beneath its surface. Oliver White, a planetary scientist at the SETI Institute in California, created a geologic map of Pluto but was not directly involved in the study. Although the features observed on Pluto's far side resemble others found in the solar system, the low resolution of the images leaves some uncertainty. Still, there is a general consensus among scientists that Pluto has geological oddities, particularly the large number of fractures on its far side, which suggest the possibility of a hidden ocean and shed light on its potential origins. Hypotheses about Pluto's ocean have long proposed that it was once a frozen body of water that melted due to heat produced by radioactive elements in its rocky core. In this scenario, when the ice melted and later refroze in the colder basin, wrinkles would have formed on the surface, similar to the wrinkles that appear on an apple left in the refrigerator. These wrinkles would have resulted from the compression of ice as it melted and expanded as it froze, creating fractures in the surface. If this theory is accurate, images of Pluto should show older wrinkles and more recent fractures. However, the images from the New Horizons mission revealed mostly fractures, suggesting that Pluto's subsurface oceans may have started as liquid and eventually froze. Observations from the New Horizons probe also revealed a giant fracture running across Pluto's near side, appearing to extend from the North Pole southward to the far side of the dwarf planet. This feature, known as Pluto fracture, likely marks the ongoing evolution of the frozen ocean, rather than indicating a sudden change in the surface. The presence of water on Pluto is further suggested by the detection of water ice on the near side of the planet, which shows signs of being impregnated with organic compounds. Although it may seem improbable on a world like Pluto, laboratory experiments have shown that solar and cosmic radiation can create complex organic compounds, including bases present in RNA and DNA. These findings bolster the theory that Pluto could harbor organic molecules and potentially support life. Additionally, the probe's observations revealed a red band at Pluto's equator, possibly composed of organic material corresponding to a region with greater solar exposure and warmer temperatures. This discovery is significant because it suggests the presence of both liquid water and organics on Pluto, two key ingredients for life. In contrast, some UFO enthusiasts have proposed alternative interpretations of these discoveries, claiming that some of Pluto's features may be of artificial origin. However, these claims are not supported by scientific evidence and remain speculative at best. In conclusion, Pluto continues to intrigue scientists and the public alike. While it may no longer be classified as a planet, the dwarf planet holds many secrets that could reshape our understanding of the outer solar system. The possibility of a subsurface ocean, along with organic compounds on its surface, suggests that Pluto is not as barren as once thought. As we continue to explore this enigmatic world, we may discover even more surprising insights into its geology, potential for habitability, and role in the broader story of our solar system. The presence of possible counterfeit designs on Pluto has sparked curiosity, particularly due to irregularities in some of its images, such as a visible smoky trail on its surface. NASA attributes this to natural phenomena, but some believe it could hint at evidence of extraterrestrial activity. Pluto, often described as a planet of contradictions, continues to captivate both astronomers and enthusiasts due to its complex and enigmatic nature. One of the most striking aspects of Pluto is its atmosphere, which, despite its vast distance from the Sun, remains dynamic and ever-changing. Composed primarily of nitrogen, with traces of methane and carbon monoxide, Pluto's atmosphere undergoes seasonal changes, expanding and contracting as it orbits the Sun. These cycles resemble the Earth's seasons, although they occur over a much longer time frame, given Pluto's 248-year orbital period. When Pluto approaches the Sun, its temperature increases, causing nitrogen ice to sublime into gas, thickening the atmosphere. As Pluto moves farther away, the frigid temperatures freeze the atmosphere back onto the surface, leading to a dramatic drop in atmospheric pressure. This recurring behavior offers valuable insights into the processes governing icy bodies, and may serve as a model for understanding similar phenomena on distant exoplanets. Pluto's surface geology is equally intriguing, featuring a mosaic of terrains that reveal its geologic history. Observations from NASA's New Horizons mission uncovered regions characterized by smooth plains, towering mountains, and deep valleys. The area known as Sputnik Planitia is particularly fascinating, showcasing vast nitrogen-rich plains with polygonal patterns believed to result from convection within a subsurface ocean. These patterns suggest ongoing geological processes, indicating that Pluto is far from being a geologically inactive world. Some of Pluto's mountains, which rise as high as 3,500 meters, are primarily composed of water ice, which behaves like rock under the dwarf planet's extremely cold conditions. The presence of these mountains indicates that Pluto has experienced tectonic activity, possibly driven by internal heat from radioactive decay or the freezing and thawing of subsurface oceans. This tectonic activity contrasts sharply with the long-standing perception of Pluto as a static, unchanging world, suggesting that it is a dynamic body with a complex history. Another point of interest is the presence of methane on Pluto's surface. Methane ice can create a wide range of colors and features, adding to Pluto's visual complexity. Scientists believe that interactions between methane and ultraviolet radiation from the sun can lead to the formation of complex organic compounds. This raises intriguing possibilities regarding the prebiotic chemistry that could occur on such distant worlds, highlighting Pluto's potential as a subject for astrobiological study. In addition to its surface and atmosphere, Pluto's relationship with its moons, particularly Charon, adds another layer of complexity. Charon is so large relative to Pluto that they are often referred to as a double system. The gravitational interaction between the two bodies results in a synchronized rotation, meaning that Pluto and Charon always show the same face to each other. This unique relationship influences their orbital dynamics and may play a role in the geological processes on both bodies. Recent studies have suggested that Charon may also harbor a subsurface ocean, further complicating our understanding of the system. The gravitational pull from Pluto could generate enough heat within Charon to maintain liquid water beneath its icy crust. If true, this would imply that both Pluto and Charon share a common history of geological activity and potentially even organic chemistry. The scientific community continues to refine its understanding of Pluto, and future missions may shed even more light on this distant world. The ongoing analysis of data from New Horizons has sparked discussions about additional missions to the Kuiper Belt, where other similar objects could provide comparative insights. Objects like Haumea and Makemake, which share characteristics with Pluto, could yield valuable information about the formation and evolution of the solar system. Understanding Pluto's complexities extends beyond its own boundaries, as studying such distant worlds can inform theories about planetary system formation, including our own. By examining the similarities and differences among these celestial bodies, scientists can develop a broader perspective on the processes that govern planetary formation and evolution across the universe. Pluto's unique composition, including its potential for organic molecules, has led to speculation about its capacity to support life. While the extreme conditions on its surface may seem inhospitable, the possibility of subsurface oceans offers a glimmer of hope. Such environments could harbor microbial life, similar to extremophiles found on Earth that thrive in harsh conditions. If life exists in these hidden oceans, it could fundamentally change our understanding of life beyond Earth. Cultural perceptions of Pluto have also evolved over the years. Once regarded as the ninth planet and a symbol of hope for discovering new worlds, its reclassification as a dwarf planet sparked debates within both the scientific community and the public. This shift has prompted broader discussions about what defines a planet and how we categorize celestial bodies in our solar system. Pluto's story serves as a reminder of the dynamic nature of scientific understanding and the importance of revisiting and refining our definitions as new discoveries are made. Ultimately, Pluto remains a beacon of intrigue within our solar system, challenging assumptions and inviting ongoing exploration. From its complex atmospheric dynamics and geological features to its potential for harboring organic molecules and subsurface oceans, Pluto embodies the mysteries that lie beyond our immediate grasp. As scientists continue to study this fascinating world, each discovery brings us closer to understanding not only Pluto itself but also the fundamental questions about life and the nature of the universe. The journey of exploration ensures that Pluto will remain a subject of interest for years to come. Pluto's unique characteristics have driven captivating scientific inquiries and hypotheses, particularly regarding its formation and evolution. One compelling aspect of Pluto is its potential to host cryovolcanism, which involves the eruption of substances like water, ammonia, or methane instead of molten rock. The presence of large smooth plains and towering mountains suggests that some geological processes may involve the release of these materials from beneath the surface. The possibility of cryovolcanism challenges conventional ideas of what constitutes volcanic activity and broadens our understanding of geological phenomena beyond Earth. Additionally, the discovery of various surface features raises questions about Pluto's atmospheric history. Scientists have observed that Pluto's surface is dotted with bright and dark regions, indicating different chemical compositions and geological processes. The bright areas are predominantly composed of nitrogen ice, while the darker regions contain complex hydrocarbons, which may form through photochemical reactions driven by solar radiation. These findings highlight the intricate interaction between sunlight, surface materials, and atmospheric conditions, inviting further investigation into Pluto's atmospheric dynamics. The study of Pluto's atmosphere has significant implications for understanding planetary climates across the solar system. Although Pluto's atmospheric pressure is very thin, it has shown variations that could be linked to seasonal changes. This behavior may resemble atmospheric dynamics seen on larger bodies like Mars and could provide insights into the climates of exoplanets with similar characteristics. The ongoing research surrounding Pluto also underscores the importance of interdisciplinary collaboration. By combining insights from geology, atmospheric science, and astrobiology, scientists are piecing together a more comprehensive picture of this distant world. As technology advances and new missions are planned, the potential to uncover even more about Pluto's secrets remains tantalizing. Each new discovery has the potential to reshape our understanding not only of Pluto but also of icy bodies in the solar system and beyond.